Hello and welcome to Algebra 1, Chapter 9.6, and today we're talking about growth and decay. So first we're going to start with exponential growth, and we talked about exponential functions in 9.5, and our growth function is one that came in along the x-axis and curved up like that. And this can model several things. It can model a population, and on a great day it could maybe model your bank account. And so the general equation for growth, y equals c times the quantity 1 plus r to the t, and we need to know what all those variables stand for. So c is the initial amount, so if it's your bank account, that's how much you put in to begin with. If it's maybe a population of deer, something like that, that's just going to be how much you start with. R is the rate of change, and you're going to want to change that from a percent to a decimal. And T is going to be our time measured in years. So we're going to look at an example here. In 2005, the town of Flat Creek had a population of about 280,000 people and a growth rate of 0.85% per year. So we want to write an equation to represent their population since 2005. So if we use our form we just wrote down, c times 1 plus r to the t, we know that they started with 280,000 people, so that goes in for c. 1 plus r is the rate, but we need to change it to a decimal. So you divide that by 100, or move the decimal to the right, and so we get 0.0085. And t is going to be t still, not changing anything, because we're going to represent any number of years after 2005. And you're always going to simplify this. So we're going to actually put this as, that's a parenthesis, 1.0085 to the t. So there's our equation for the first part. Using our equation, what will be the population in 2015? Well, how many years after 2005 is that? It's 10 years. So we're going to take our equation and we're going to put in a 10 for our t, and we're going to type this into the calculator now. And try and make sure you can get the correct number in your calculator. I get 304,731.29, and we can't have 0.29 of a person, so let's just make it 731 people. So we wrote our exponential function in the first part, and we used it in the second part. So let's try that one more time. Computer use has risen 19% annually since 1980. If 18.9 million computers were in use in 1980, write an equation for the number of computers in use for t years after 1980. So again, we're going to use our general equation we wrote down. And c is the initial amount, so we're going to put 18.9, and that's going to stand for million. And we have 1 plus our annual rate is 0.19 because you want it as a decimal, to the t power, because this is going to be for any year after 1980. Add 1 plus 0.19, and there's our function. And then we're going to use it. So 2015 is going to be 35 years later. So we're going to plug in a 35 there, and we're going to use our calculators. And I get it, so in the calculator it comes up as 8,329.24, but that's going to be million computers. So if you still have that in your calculator, you can actually times it by a million. So we would get 832924147 computers. There would be 1,000 million. So there. Oop, I put my. Sorry, there we go. So there's our 8,329 million computers, and that's the whole number out there. So the next kind of specific exponential growth equation we can talk about is compound interest. And this really models what you have already written down as y equals c times 1 plus r to the t. This is very similar. We've just critiqued it a little bit. So we've used a instead of y, and a is just your current amount. P is the principal. It's the money you start with, so still the money you start with, still what C was standing for, we just changed it to P. 1 plus, now compound interest is you earn interest so many times a year, and then you earn interest on your interest every time you earn interest, which is awesome. And so it's an annual rate, which is why we divide it by n, the number of times it's compounded per year, the number of times you get interest per year. Let's say it's a 12% annual rate. Well, if you get interest 12 times, you're getting 1% each time then. And our exponent is n times t, so the number of times it's compounded per year times the number of years. So make sure you have this equation written down, and then let's use it. So when May was born, her grandparents invested $1,000 in a fixed rate savings account at 7% compounded annually. The money will go to May when she turns 18 to help with college. What amount of money will May receive? So you wrote A equals P times 1 plus R over N to the NT. And so we're looking for the amount. So A equals, P is how much they started with, which is 1,000. 1 plus, R is still rate as a decimal, so 0.07. N is how many times it's compounded per year. So it's compounded annually, meaning it's compounded once per year, to the 1 times. T is how many times it's going to, how many years, and that's going to be 18. So before I put that in my calculator, I'd probably do a little bit of cleaning it up. 0.07 divided by 1 is just 0.07. Plus 1 is 1.07. And 1 times 18 is 18, and that will make it easier for you to type into your calculator. And you should get $3,379.93. Make sure when you're dealing with money that you correctly round to 2 decimals. So the last thing we want to talk about real quick is exponential decay. And when you graph exponential decay, it comes down like this. So this would be if you had some sort of radioactive element and it has a half-life, it's going to decay. And so same exact equation we were talking about earlier, with the exception that instead of a plus sign in the middle for growth, we have a minus sign in the middle for decay. So everything stands for the same values, and let's see if we can use this. During an economic recession, a charitable organization found that its donations dropped by 1.1% per year. Before the recession, its donations had been $390,000. So we want to start by writing an equation. So y equals c times, so since it's a drop, this is where we get our 1 minus r. And so C is $390,000, and this is going to be 1 minus 1.1% as a decimal is 0.011 to the T, and we're going to do a little bit of cleaning up and do 1 minus 0.011 and get 0.989 to the T. So there is our equation. And then it asks us to use that equation to estimate the donations 5 years after the recession. So we are just going to plug in a 5 for our exponent. And again, grab that calculator. So just numbers that you really don't want to do without a calculator. And so I get, talking money, got to put a dollar sign, $369,016.74. Again, make sure that you're accurately rounding to 2 decimals when we do money. All right, that is 9-6. We are now done with Chapter 9. Let me know if you have any questions. And if not, I will see you in class. Have a great day.